This is Unit 5, Section 5.1. We're going to look at discrete and continuous variables. And so this will start off our unit on random variables, so that's kind of why we're introducing them. And so we want to make sure that we are following along. We should finish up this unit before winter break. And so we're going to talk about what a random variable is and then how we can combine them, manipulate them, and find probabilities associated with them. So a random variable to start out with. A random variable is a quantitative variable that describes the outcomes of some chance process. So we've, in previous units, called it a quantitative variable. This is also called a random variable. And when we have a random variable, it's just the outcome of a chance process. So when we have a probability distribution, we have all the possible values and their probabilities of a random variable. So what we have is a distribution that says, okay, if this is one of the possible values, here's the outcome probability. If this is another possible value, here's their probability. And so as we start looking at some tables typically that describe our random variable, we'll see that it represents every possible scenario and then a probability associated with that scenario. So we're going to talk about two different types of random variables, a discrete random variable and a continuous random variable. So the first one, a discrete random variable, is a random variable with a finite number of possible outcomes. And so this would be like your shoe size. Okay, shoe sizes, you can get an 8, an 8.5, a 10, a 10.5, but you can't get a 10.1. You can't get an 8.3. There's a finite number of possible outcomes. It's not a continuous spectrum that you could get every possible outcome there. So this is just a set number of possible outcomes, but shoe size is still a number, so it still has a quantity there, and it still makes sense that we could find the average of it, taking the average shoe size. So one of the things that we might want to be asked or might want to find or might be asked to find is our expected value. And so there's two different notations for that, E of x or mu sub x. Both of these represent the same idea of the expected value. So if I were to pick a shoe size, what would I expect that shoe size average should be? So it's kind of like that idea of if I have all the possible values, so maybe for adults we have like size 4 to size 15, okay, if we put men and women there. What would be the expected value of the shoe size? And so it says the average of a discrete random variable x, which is also an average of the possible values of x. It does not have to be exactly one of the possible values and is found by multiplying each possible value to its probability and adding then the products. All right, so here's our two notations, and we're going to take observation 1 times its probability, the possible value times its probability, and then add it to the second observation times its probability, and so on until we've done all the observations times their probability. When we add those up, that's our summation sign. When we add those up, that will give us our expected value. All right, so now we have an idea of mean. This is what I would expect to observe here. The second thing that we could calculate or might be asked to find is the standard deviation, a mean and a standard deviation here of our random variable. The standard deviation of a discrete random variable is the typical distance from the mean. So that definition is still the same. And so when we want to find that, the standard deviation of x, so we have our notation here, is equal to the square root of standard deviation squared. Okay, this is our variance. Okay, so variance is standard deviation squared. And how we calculate our average here is by taking the square root of the sum of every observation minus the mean, which we find doing this, squared times the probability. And so this is how we do it, and it is on our formula sheet. So if I look at our formula sheet, I'll pull that up here. This is one of the formulas that's given to us here. So if we looked at a random variable, okay, and maybe we have it down here. Now I have to remember where it is. Maybe this one isn't given to us. And again, that's where I rely a lot on not the standard, not the formula sheet here. So I'm double checking. All right, so the reason that I don't know that it's on there or not is because we typically use our calculator. And I'll show you how to find that to make sure that we are able to find the average and the mean using our calculator. But these are the formulas that we use. All right, so in our example, we're going to focus on this context for most of our section here. It says the APGAR score shows a newborn's level of health by assigning a 0, 1, 2 scale to each of 5 criteria. Skin color gets a 0, 1, or a 2. Heart rate gets a 0, 1, or a 2, and so on for these different categories. And then adding those 5 numbers together is what gives it the APGAR score. So a baby's APGAR score is a whole number ranging from 0, which means low, to 10, which is a high score. So what APGAR scores are typical? To find out, researchers recorded the scores of 2 million newborns in a single year. Imagine if we selected one of those newborns at random. We're going to define discrete random variable x to be the APGAR score of a randomly selected baby. The table below shows the probability distribution of x. All right, so again, here is x. These are the possible values that we could have for an APGAR score of a randomly selected baby. They could have a 0, a 1, all the way up to 10. And then here is the probability associated with each of our observations. So we have 0.001 all the way up to 0.053. Can we show that this probability distribution is legitimate? Okay, so there's 2 things that we're going to check. The first one we're going to check is each probability is between 0 and 1. Okay, so if I check this, every one of these is a probability. Okay, and then the second thing that we're going to check is, do all the probabilities add up to 1? And so when we look at this, now we're going to put this in our calculator, 0.001 plus 0.006. So I'm just going to add these up on my calculator. So I've grabbed my calculator, 0.001 plus 0.006 plus 0.007. And when I sum all these together, they equal 1, which means this is also met. So because of these 2 things, this is a legitimate probability model. All right, so we have 100% of the observations accounted for and all of the possible outcomes. This is a legitimate model. So to follow up, it says doctors decided that a baby is considered healthy if they have an APGAR score of 7 or higher. So what is the probability that a randomly selected baby is healthy? All right, so what they're asking us is what's the probability, and we're going to say of X, an APGAR score, is greater than or equal to 7. All right, so when we do a discrete random variable, each one of these observations is independent. So you can't be in mutually exclusive. You can't be in a category and in another category at the same time. So if we want to find these probabilities, we're going to add together those 4 observations here. The 0.099 the 0.319, 0.437, and the 0.053. So when we're doing a discrete random variable, we can find and combine observations because they're not dependent on each other and they're mutually exclusive. So if I add these together, I get 0.099 plus 0.319 plus 0.437, and lastly 0.053. I get there is a 0.908 probability that a randomly selected baby would be healthy. Okay, that is an amazing thing. That means 90.8% of babies are considered healthy when they're born. My poor little goddaughter was born 2 months early, and she was a score of 1. She had poor skin color. She had a low heart rate. She had very little muscle tone because she was so little. She was not breathing, and she had no response when stimulated. That was a really scary time for her mom and dad. But the nice thing is, like again, 90% of them are going to be born healthy. And that's kind of the miracle about that. All right, continuing on this one, it says calculate. I think I skipped a part here. So it says, let's make a distribution of the probability distribution and describe it, because I think I skipped part of the notes there. Oh, I gotta scroll down. Here we go. All right, make a histogram of the probability distribution, describe the distribution. So again, anytime we're asked to describe a distribution, we should be thinking our 4 key aspects here. And then we're going to make our probability distribution by taking our table and converting it here. So if this is our APGAR score, and then these are the probabilities of that observation. We can have a 0, a 1, a 2. I might have to make this a little skinnier here. Give myself some room to get to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then on this side, we have the largest one is 0.43, so maybe I'll count by 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5. And then we create our graph. And so looking at 0, the APGAR score is 0.01. So I'm just going to like kind of draw a line there. And then we have 0.06. So maybe like 2 lines here. I mean, it's just going to be very low. Same thing for at 3. Same thing kind of here at 4, 0, 1, 2. 3's here. 4, we kind of jump up just a little bit more. So again, I'm just kind of making this very little here. 5, we get up to 0.02. So now we should be just a little bit taller. Maybe like a quarter of that box here, almost, or a fifth. And then we get to 0.038. And then we get to 0.099. So now we're almost all the way up to here. And at 8, we're at 0.319. So all of a sudden we go up to here. And then we go to the next one, 0.437. That's the highest here. And then 10, we're back to 0.05. So about half of that. All right, so if I was going to describe this, okay, skew to the left. So most babies are born with a higher APGAR score. Right? That is using context to tell you it's skewed to the left. There doesn't appear to be any outliers, but possibly an outlier down at the bottom. So maybe I wouldn't address this. No apparent outliers. But again, we're eyeballing this distribution. We're not doing any calculations here. The center, I would say kind of maybe 7 or 8 here as I look at it. So maybe 7 as my balancing because it has this long tail over here. maybe around 8, kind of to balance that out. So I would say center the typical APGAR score is around 7 or 8. And the scores vary from 0 to 10. All right, so I've addressed shape, I've addressed outliers, center, and spread, all in context. And so now that I'm jumping ahead here, now we have calculate and interpret the expected value. So we estimated it visually to probably be around that 7, 8, kind of looking at where that is and how much we get tipped over, but it's probably right around here. So if we actually want to calculate that, we have our formula that says, okay, take every observation times its probability and add those up together. So if I wanted to do this by hand, I would take 0 times 0.001 plus 1 times 0.006 plus 2 times 0.007 plus 3. And again, I'm just going to keep doing this each piece until I get all of them. You should ask your parents, maybe they remember what your APGAR score was. Again, my parents did not remember anything because they did not know they were having twins, and so that was a bigger deal than anything else that could have been possibly happening at that moment. My sister was born, and she did not weigh the expected 9 pounds that they thought she was going to weigh, and so they checked for another heartbeat, and out I came. So checking healthiness was crazy, but I doubt my mom would recall anything about what happens that day other than the fact that I surprised her. All right, I got that all written out, and so I put this in my calculator. And so to calculate this, I'm going to just add up all these pieces, typing it in carefully. And when I put that in my calculator, I get 8.128. So I've calculated the interpretation would be on average. Okay, that's our typical. So on average, we expect a randomly chosen baby's APGAR score to be 8.128. Okay, keep in mind that this isn't a number on our scale, so we don't round expected values. Just like the typical household is like a 4.2 nuclear family, this is the same idea. Even though there's not like 0.2 of a baby running around in everybody's house, that's still the expected value. It just tells you it's not exactly 4, it's not exactly 5. We don't round here, we just keep it exactly that same outcome. Okay, now keep in mind, like at some point we have to cut off. I guess we don't round up to a observation or a value on our probability distribution. So even though we thought, okay, it's close to 7 or 8, which it pretty much is there, we don't round to one of those observations. All right, so on the second part, it says calculate and interpret the standard deviation of the APGAR scores. All right, so this is where we're going to take our standard deviation, and I want to do this on our calculator. So we already found the mean by hand, but the calculation for a standard deviation, let's do on our calculator. So remember, type these things in with me so that you get the same thing. It also helps you verify that I'm doing it correctly and getting the same thing as you. Just like you guys make mistakes, I can too. We all try not to. All right, so I'm going to get this loaded up here. And so what we're going to do is we're going to enter in the data, so our values, we're going to enter that into list 1. All right, so I'm going to go to stat, I'm going to edit, and I have cleared list 1 out, and so then I'm going to enter in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Oh, I messed it up already. All right, so now we have 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, and then I'm going to put in list 2 the probabilities. So this is the new part, is that these are associated together. All right, so I've entered in all the probabilities associated with each outcome. And so the new part that we're going to do, just like we did before where we wanted to find mean and standard deviation, we would use one variable stats. And so if I look at my menu here, I've list 1, this is where all my observations are, but this is the new part. Our frequency list, each one of these doesn't happen equally. 0 does not occur at the same frequency as 10. We need to associate those with their probabilities. So in the units that we did before, like in unit 3 or unit 2, we had every observation. Okay, keep in mind that in this data set, there were 2 million newborns that they measured the APGAR score on. We are not going to enter in 2 million numbers into list 1. They've told us, here are the possible outcomes, here's the frequency or the probability associated. So I'm going to use second 2 and associate my list 1 with list 2, and then enter. All right, so notice that the very first number is that same 8.128 that we got by doing this by hand, but now we have a standard deviation here that we didn't do by hand, and it can calculate for us. So notice that it's not giving us S sub x, it's giving us the sigma x, and that's because this is not a sample, this is the entire population. This is every possible outcome that we had. And so when we look at this, we're going to get this standard deviation. So we get a standard deviation that says we have 1.4372. So we've calculated it using our calculator this time. And to interpret it, it would say a randomly chosen baby's APGAR score. Okay, so again, bringing in that context again, will differ from the expected by about 1.4372. And so as we look at this, we could have said, going along with our standard deviation interpretation from unit 2 and 3, we could have said the typical distance from the expected is about 1.4372 for a baby's APGAR score. So as long as we're talking about the baby score, there's our context, and that it's the typical distance from the mean. So it differs from there, it's the typical distance from. We need that in our interpretation. All right, a different example, moving away from the APGAR score, it's moving to kind of betting in roulette. And so it says one wager players can make in a roulette is called a corner bet. So to make this bet, a player places his chips on the intersection of 4 numbered squares on the roulette table. If one of these numbers comes up on the wheel and the payer bet $1, I think that's supposed to be player here, the player gets his $1 back plus $8 more. Otherwise, the casino keeps the original $1 bet. If X is equal to the net gain from a single $1 corner bet, then the possible outcomes are you lose your dollar or you get your dollar back, which is 0 plus 8. Here's the probability distribution. So here's X, here's P of X. All right, so when we're looking at our distributions, we can look at any casino game, any chance game, and they will have probability tables for this. And so what if this player were to make this $1 bet over and over and over again? What would we expect the player's average gain to be? Maybe if it's thinking here. Give me a table. And so this is the one that you've probably seen on movies where they have a little ball that they throw into a wheel and the ball goes and lands in one specific place. And so what we're looking at here, and I'll just take a copy of this one. Okay. What we're looking at here is this idea of a bet called a corner bet. And so a corner bet is where you would place a chip. So pretend I have a chip here. So if I place my chip, so say this is my $1 chip, I would place it here on the corner. This is a corner bet, meaning when the ball goes round and round and round and round and round and round and round, I've really bet on 12, 15, 14, and 11. Or I could place it here. And again, the dealer will put the ball in here and spin and spin and spin and spin and spin. And then we have the options. I could win at 17, 20, 19, and 16. There's lots of different bets that you can make. You could say, I'm going to put my $1 bet on 1 through 18. Okay, so then any number 1 to 18, you win. But there's a different probability associated with that and a different payout. So every bet in roulette has a different payout. You can also do 2, where you just bet these 2. You can do colors. You can do odds and evens. You can say the first 12 here. You can do the second 12. Again, I told you that I really like going to Vegas, but I don't like losing money. So unless I understand the betting, I won't play. Or unless it's like a penny. Like I'll go with a penny, or I have friends that'll be like, go take a 20, put 20 on red. So I'll go to our roulette table, put their 20 on red. If they win, I ask them if they want to keep going. If they lose, I say, I lost your 20. So sorry. So if they make this corner bet, so if we take this and we put it here or here, anywhere on here, just making any corner bet, what's the probability or what's the expected gain? All right, so this would be our expected value. So any expected value, average idea here, we're going to take the sum of every probability times its observation. So when I do this, I only have 2. So I have -1 times 34 out of 38, okay? So on here, there are 36 pieces here, and then there's 0 and double 0. Yep, this one only has 0. All right, so this one might be a different kind of board here that I grabbed, but typically there's one on this side that's green as well, that is double 0. So there's 38 on a typical roulette table. So I would lose my dollar on here and here. If it lands on one of these, I've lost my money. If it lands on 0 or 0, 0, I've lost my money. So on all of these, 34 out of those 38 spins, I will lose my dollar. Or I could gain $8 if it happens to land on these 4. So if I place my chip there, there's a 4 out of 38 chance that I will gain money back. And so when I put this in my calculator, -1 times 34 out of 38 plus 8 times 4 out of 38. I get -0.0526, da-da-da-da-da-da. All right, so I'm not going to round up to -1 or 8. Again, we don't round expected values here. So as we're looking at this, what would be the player's expected average gain? And so what this tells us is that the game is rigged against us, okay? The average game, if we played this over and over and over and over again, what's the average gain? You're going to lose a nickel every time. So on the expected value, is a loss. So that means you can expect to gain negative money if you play this over and over again, which is again why if you understand the betting, you know that it's against you. So if you get up at all, you should quit or take back all the money that you started with and only play with winnings. That way you never go lower than what you started with. All right, so this is one game, and I wanted to find us a table that has, there it is. Okay, so maybe this one's more clear because I think I was looking at a different one. So if we look at this table, now it has the 0, 0, because I was like, I think there's a European board and an American board. 0 and 0, 0 are the two, and they're across from each other. And then here are all the ones that we can bet on. And again, I can put my chip here and just do on the first third, and that's a different payout than if I bet on 1 through 18, and so on. So we'll do a couple of different casino games just looking at the payouts here, and the first one is kind of looking at roulette. So right now we're looking at the corner bet, but we'll continue looking at a couple different bets as well. So make sure that we're kind of understanding our idea today that we're looking at a discrete random variable. And so we have the probability table, and we can find probabilities by adding up those scores. We can find expected and standard deviation on our calculator. Let me know if you have any questions.